This is Dr. P. Jaikanth Yadav, working as assistant professor in Institute of Aeronautical Engineering College. And my course title is Complex Analysis and Special Functions. Today my topic is Introduction of Complex Line integrals. So we are going to learn here performing line integral of complex function. Okay, this is the definition, some introduction of the line integral. So line integrals are single integrals which are obtained by integrating a function over a curve instead of integrating over an interval. Okay, right. So here we are going to perform line integral. The line integral means this is the single integrals, okay, which are obtained by integrating a function over a curve instead of integrating over an interval. Okay, these are also single integrals. Next, here to define these line integrals, we are going to explain, consider a continuous function f of z. So we are taking f of z is a continuous function of a complex variable z whose real part is x and imaginary part is y. Defined for all the points of curve C. It is a curve C having endpoints A and B. Okay, divide the curve C into n parts at the points. So we are taking A. In A we are taken as P0 at Z0 and P1 at Z1. P3, this is the point 3. We are dividing the curve C into n parts at n points. Okay, these are the points. At these points we are dividing. You can see here, I will show the graph. Here there is a complex plane. A horizontal axis we have taken as real part of the complex variable, that is x. Here z is a complex variable and its real part is x. That's why I am writing here x. And vertical axis represents imaginary part of the z. Here imaginary part of z is y. Okay, this is the complex plane. And we are taking a curve whose endpoints are A and B. So this is one endpoint, another endpoint is B. Here I am going to take the curve as in this form. Okay, this is the curve C. This is curve C. Okay, so we are dividing the curve C into how many parts? We are dividing into n parts. So to divide this curve into n parts, we need n plus 1 points. Okay, so here the point A, we taken it as Z0. Okay, at B I am taking it as Zn. Okay, so in between we can find Zi minus 1 and this is Zi. The function value at Zi minus 1 denoted by P I minus 1 of Zi minus 1. This is the function value at that point. Okay, similarly at Zi, function value at Zi is Pi Zi. Okay, right. So this is the curve and these are the points A and B, endpoints of the curve C. Okay, now you will see how it is defined. Here we will take delta Zi. Delta Zi defined as Zi minus Zi minus 1. It's the difference of two consecutive numbers in the points we are dividing. So Zi to Zi minus 1, two consecutive points. So this is the length of the interval, ith interval, you can say. And there is another point we are taking. This is gamma I. Be any point on the arc pi minus 1 and pi. Okay, any point on the arc. So we are dividing the curve C into how many parts? N parts. Out of n parts, we have different arcs are there. How many arcs we will have? N arcs. So this is the arc number ith arc. So there is a one point on the arc which is gamma I. So in this case, the limit of the sum, we are taking f of gamma I. Gamma is any point on the arc, and delta zi. So we are multiplying these two. Here I is there, subscript I is there, and we are taking this product for I is equal to 0 to n. So this is the sum. This is the sum containing how many terms? N plus 1 terms. Okay, here as n approaches to 0, this limit of the sum as n approaches to 0 is called line integral of f of z. Line integral of f of z taken along the path C. So this we are denoting with integral over C fz dz. This is integral over C fz dz. Okay, this we call it as integral of the complex function f of z over the curve C. Okay, this is the definition of line integral of a complex function f over the curve C. Next, so here another case. In case the points A and B coincidence, so that the curve C is a closed curve, then the integral is called contour integral and is denoted by integral over C fz dz. Here you can observe this, So this cycle we are going to write on the integral symbol only when the curve C is closed curve. So what is meant by closed curve? In a closed curve, we can observe that starting point and ending points are same. So if you are performing integration along the closed curve, that integral we called as contour integrals. Okay. Next, contour integrals. Next, if you take f of z, whose real part is u, usually it is a function of x and y. X and y we know. X is the real part of complex variable and y is the imaginary part of complex variable. Plus, and here we are taking imaginary part of f of z we are taken as v. V is also usually a function of x and y. So then, since we know dz is equals to dx plus I dy, so we all know complex variable z, which is x plus iy. Now I want to find dz, means derivative of z. Derivative of z will be dx plus I dy. I am applying derivative operator on both sides. Okay, so you will get dx plus I dy. So in this case, we have integral over C fz dz can be written as there is f of z. F of z is simply I am writing u plus iv. This is simple form. And dz can be written as dx plus I dy. Right, and we have integration along C. If you divide the real parts and imaginary parts of this product of these two complex numbers, this is a one complex number and this is also another complex number. If you divide the real and imaginary parts, you will have this term, and you also have imaginary part, whose imaginary part is this much. Here what we can observe that evaluation of integration of a complex function evaluation of line integral of a complex function can be reduced as two line integrals of real functions. This is a real function. Two line integrals of real functions. This is one line. This is one. This is one integral of real function, and this is also another integral of real function. So we are writing a complex integral as we are splitting the line integral of complex function into two parts. So real integral, okay, and imaginary part also we are writing in terms of integral of real function. So we are going to use this formula to evaluate for evaluation of line integral of complex function. We are going to split into real part and imaginary part. Right. Now you can see here, note, the value of the line integral depends on path unless the integrand is analytic. Right. You can observe that the value of the line integral depends on the path. Okay, suppose there is a complex plane x and this is y, imaginary part. Here there are 2 points. There are 2 points of the complex, 2 points in a complex plane. Say it is a complex number, and the small b is also a complex number. So I want to perform integration between a and b. So here there is a path connecting these 2 points. This is curve C1, and we have another curve. C2 curve. This is also connecting a and b. So, and there is a function, we have f of z. In this case, line integral of f of z from a to b. So here I want to discuss about on the curve C dz. Here integration of the complex function f of z along C1, it should be equals to integration of f of z along C2. Okay, this is possible only when fz is analytic. In that case, these two are same, and this equality may be fail if fz is not analytic. In that case, we are not giving any assurance both are equal. So this is equal only when this is equal if both integrand, if fz is analytic, in that case only. Right. Now there are properties of line integrals here. When the same path of the integration is used in each integral, then so we are using same path of the integration. Here there is a complex plane a and b. There is a curve C. This is curve C, and there is a point A and B. Here, if you take integration of f of z dz from a to b, and this value is equals to negative of integration from b to a fz dz. Here, when I am evaluating integration, I am using curve C. On this, here path is same. In the both integrals, path is same, but endpoints are different. In that case, we will have integration of ab fz dz is negative of b to a fz dz. In this case, path is same. Next, second point. If C is a point on the arc joining A and B, then okay, here there is a point, and here A and B, and there is this is my curve C. This is curve C. There is a point small c. there is a real axis and this one is imaginary axis. So integration, you can see integration of a to b fz dz can be written as integration from a to c fz dz plus integration from c to b fz dz. Okay, right. Next, we will do one problem here. Evaluate integral. Here, the endpoints of the endpoints from where to where we have to perform integration. We have to perform integration here is z value 0 to z value is 1 plus I. Here integration, here integrand is given as x square plus 2xy plus I times y square minus x dz. Here along which path is given here? Y is equal to x square. Now, you know, there is x is a real part of the complex variable z and y is the imaginary part of complex variable z. So the real and imaginary parts, the relation between real and imaginary parts is given. Y is equal to x square. You know, y is equal to x square represents parabola. So it is a parabola symmetric to which axis? Y axis. So this is y is equal to x square called. In the complex plane, here you can assume it is a complex plane. So from where to where I need to perform integration? I have to perform at this point z is 0 and there is another point in the curve y is equal to x square. This point is nothing but 1 plus I. This is 0 and this is 1 plus I. Okay, this is 1 plus I point in the complex plane. So I need to perform integration along the curve C. This is my curve C. Okay, so the equation of this path is y is equal to x square. So here given, here what is f of z? You write f of z, write imaginary and real part, real parts and imaginary part. Real part is x square plus 2xy and imaginary part is y square minus x. So here along the path, which path is given? Along the path y is x square. Okay, so we are performing integration on this path. In this path there is a relation between x and y. This is the relation. Now I can write the derivative of y. Derivative of y will be what? It is 2 times of x dx. Right? On this path, the derivative of y will be like this. So that I can find dz. I can find dz. dz is required because here we need to, dz is there. I want to write dz in terms of real and imaginary parts. So dz the real part is dx and dz imaginary part is dy. So here dx is same, I can write like this only, and I dy can be written as 2x dx. Okay, so this is simply we can write as 1 plus I times 2x dx. So dz is this much. It comes in terms of x. Observe this. Next to fz and fz. How we can write fz? By using this relation between x and y. Y is equal to x square. Here I can write f of z as x square plus 2x y is there, y replaced by x square. Okay, plus I is there, x square whole square minus x, right? So this value is what? This is x square plus 2x cube plus I times x to the power 4 minus x. This is f of z. Here what you are observing here, dz comes in terms of x and fz is also come in terms of x. So we need to find how x is varying from z is equal to 0 to z is equal to 1 plus I. At z is equal to 0, what is x value? Means real part of z. When z is 0, real part of z is also 0. Right? And when z is equals to 1 plus I, what is real part? Because z is, we know, it is x plus iy. In this case, what will be x? X will be 1. Because real part at 1 plus I, real part is 1 only. Here, x varies from 0 to 1. 0 to 1. So therefore, I need to find what is fz dz. This is required when I am calculating integration. So here I know what is f of z is already I know, which is x square plus 2x cube plus I times x to the power 4 minus x. Next I am going to write dz. Dz also I am writing here, that is 1 plus 2ix dx. Now I want to write it as there is a product of two complex numbers here. I want to write first of all real part, then imaginary part. So I will have x square plus 2x cube. 2x cube. Next I want to write imaginary part. This is minus 2x x to the power 4 minus x. Okay. This will be the real part. Okay. Plus I times here you can see so I can write dz here, dx here, plus I times imaginary part. I am going to calculate now. Imaginary part will be 2x square plus 2x cube. 2x cube. Next plus x to the power 4 minus x. Okay. Yeah. Into dx. Right. So this is fz dz. Now I am going to evaluate integral now. Therefore, integral fz dz and z varies from 0 to 1 plus I. This I write first to fz dz. Fz dz. It is x square plus 2x cube and it is minus 2x to the power 5 over 5. So plus 2x square. 2x square dx plus imaginary term, imaginary part. So here it is, you will see how much it is. 2x square plus 2x cube plus, okay, I write 2x cube first. 2x cube plus 4x to the power 4. 4x to the power 4 to the power 4, then x to the power 4 plus x to the power 4 minus x minus x dx. Here you can observe that dx is there, means x variation we want. So here we'll take all this term at one place, and here we'll take dx is there. So we need to take one x variation. X is varying on the curve, on this curve, when z equal to 0 to 1 plus I. How x is varying? It is varying from 0 to 1. Now we will simplify this term. 0 to 1 minus 2x to the power 5 plus 2x cube plus 3x square dx. Now I am splitting this integral imaginary part, integration from 0 to 1. Here it is 5x to the power 4 plus 2x cube minus x dx. Minus x dx. So it is, we will perform integration now. For the first term, you will get minus 2 by 6 x to the power 6, and x varies from 0 to 1, plus 2 by 4 x to the power 4, x varies from 0 to 1, plus 3 by 3 x cube from 0 to 1, plus I imaginary part. 5 by 5 x to the power 5 from 0 to 1 plus 2 by 4 x to the power 4 from 0 to 1 minus 1 by 2 x square from 0 to 1. We will simplify this. Minus 1 by 3. Here you get 1 plus 1 by 2. Here you will get 1 plus 1 only plus imaginary part. Here you will get 1 only for the first term, and 2 1 by 2. Okay. Here you can get minus 1 by 2. Okay. So finally, what we are getting here, minus 1 by 3 plus 3 by 2. This is real part, and plus here you can get only I. Yes. Here we will get only I. Now we are getting LCM is 6, and here you can get minus 2 plus 9 plus I. This is nothing but 7 by 6 plus I. So this is the required answer. So we are getting a complex number whose real part is 7 by 6 and imaginary part is 1. So we are performing integration of the given function f of z, and which varies from 0 to 1 plus I, and we are getting its answer is 7 by 6 plus I. Okay. Similarly, you can do integration of this. I will do only first part. Okay, and this I will do. So I am performing for this integral. We need to perform integration from 0 to 1 plus I. Clear? So it is two paths are given here. Now I am doing integration along first one I am doing here along y is x, and y is x. What is dy? Dy becomes dx only. So that what you can do? So that you can write dz as dx plus I dy. This is usual, but we know d into dy. So it is dx plus I dx. Simply it is 1 plus I times dx. I am performing along y is equal to x. Okay, and how I can write x square minus iy on y is equal to x square? I can write it as x square minus I times x. Okay, therefore what is this? X square minus iy times dz can be written as x square minus iy, and dz can be written as 1 plus I times dx. So you write as real and imaginary parts. So here first real part will be x square, and imaginary part. So this is real part. X square plus y will be the real part, and I will write now imaginary part. It is x square imaginary part. Okay, it is x square minus y. X square minus y, and both term having dx. Now we know what is y. Y is nothing but x. So I can write x square plus x plus I times x square minus x dx, since y is x. Okay, so what you are observing here, x square minus iy dz comes in terms of x only. Okay, so here we are performing integration path is y is equal to x line, y is equal to x. So from this is z equal to 0, and there is a point at z is equals to 1 plus I. Okay, this is our path of the integration is this straight line path. Now we will perform integral from 0 to 1 plus I x square minus iy. Dz is, I'll write integral here x square plus x plus I times x square minus x. Okay, for both we have dx. Okay, you can observe here it comes in terms of x, and at z is equal to 0, x value is 0. At z is equal to 1 plus I, x value is 1. In this way you have to write. Now you will have integration from 0 to 1 x square plus x dx plus imaginary part integration from 0 to 1 x square minus x dx. So if you perform the integration for the first term, you can get 1 third plus 1 by 2. This will be the real part, and I times here you will get 1 third minus 1 by 2. So finally real part will be 5 by 6 and imaginary part will be minus 1 by 6. So real part is 5 by 6 and imaginary part is minus 1 by 6. This is the required answer. Then we performing integration of x square plus iy dz along this straight line path. Y is equal to x. You will get this numerical value. Similarly, if you take along the path y is equal to x square, you can do in the similar fashion. So you know the relation between y and x, and we can find dy as I described in the previous problem, and this problem also I described. Okay, it will also come in terms of x, and find the variation of x and calculate this. Okay, in this way we will evaluate line integrals along a curve, on the curve from certain point to another point. Okay, similarly you can also do this problem. Here real part is given, which is x minus y, and imaginary part is x square. So here we have to perform integration from z equal to 0 to 1 plus I, same. But here and we need to find the path first. The path is straight line path. So in the complex numbers, it is x and this is y, and this is z equal to 0, and this is z is equals to 1 plus I. So straight line means it is straight line passing through these 2 points. Straight line passing through these 2 points is what? It is nothing but y is equal to x straight line. So here you have to perform along the path y is equal to x, you need to perform integration, because straight line passing through z is equal to 0 means 0, 0 to z is equals to 1 plus I is nothing but 1, 1 is how we can write y minus y1 is equals to y2 minus y1 by x2 minus x1 into x minus x1. You can get as y is equals to 1 by 1 x minus 0. Here also y minus 0. So you can get as y is equals to x. So this is the straight line path. Here we are taking y is equal to x. Use the same procedure. You can evaluate line integrals. Okay, this is called complex line integrals. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.